So, good afternoon, everyone. Today I am going to talk about our recent work on how the frustration, not in spin but in charge, can exhibit the truly exotic quantum phases as revealed by the modified extended Hubbard model. So, this is the outline of my talk. I will explain all of this explicitly. As you all know that the strongly correlated electron system are a treasure trove of exotic phenomena starting from high temperature superconductivity to magnetic and charge order states. Since decades, Hubbard model and its extended version play a crucial role to understand this. But this model takes only the direct interaction like on-site Coulomb repulsion which is U and nearest neighbor Coulomb repulsion which is phi. However, there is another player which is often overlooked and it is the charge dipolar interaction. And it creates when the mobile charge induces the dipole moment to the nearby atom or molecule. And it is not just theoretical, it is relevant in real material like organic charge transfer salt or transitional metal oxide, and also relevant in the cutting edge experiment with ultra cold polar molecule where interaction term can be highly tunable. So our central question is that what new physics can emerge when you introduce the charge dipolar interaction and the frustration that comes with it. So to build the intuition of the system, we start with the extended Hubbard model. So as you all familiar with this Hamiltonian, so it has the hopping term which is T, the on-site Coulomb repulsion which is U, and nearest neighbor Coulomb repulsion which is phi. Zeron, van den Brink et al. They first derived the form of this charge dipolar interaction, and according to them the Hamiltonian is looking like this. So basically it affects in three ways. So it screens the on-site Coulomb repulsion by an amount of 4p, it creates the next nearest neighbor Coulomb repulsion, and this is the chemical potential which shifts the energy level. Before going to further, I want to emphasize that the frustration can arise in different way in a strongly correlated system. The most familiar example is the spin frustration in a triangular lattice. So in a triangular lattice with antiferromagnetic bond, and so if you fix this pin, so this pin tries to align this in an antiferromagnetic arrangement, but in this pin it doesn't know where to go. It is aligned in the up or down. This creates the geometric frustration in this system. But in our system, frustration arises in different way. It is not because of the geometry of the system, it is because of the different interaction term in our Hamiltonian. As I already told you that in our Hamiltonian we have U, V and P. So U tries to avoid the double occupancy. V tries to separate charge between the neighboring side. And because of this 2p term, electrons tries to avoid the next nearest neighbor term. And they all are competing with each other. And electron doesn't know where to sit. And this creates a competition. And we call this competition as a charge frustration. So to build the intuition of the system, we start with the atomic limit. And we can solve everything exactly by comparing the energies between different charge segments. And you can see we have obtained the rich classical phase diagram. So we have the spin density wave phase, which is nothing but a Mott insulator phase. We have a two-side or four-side periodic charge order state, which we call charge density wave 1 and charge density wave 2 phases. And we also have the three-side periodic charge pattern, which we call the ferroelectric phase. So, and it also breaks the inversion symmetry of the system. But notably, around the boundary between the charge density wave 1 and ferroelectric phase, we have a degenerate charge density wave 3 phase appears which have 8-side periodic charge pattern. This already tells us that region around the ferroelectric phase is highly frustrated. There are many states which are competing for dominance, and we call this region as a frustrated I region. Of course, the real world has quantum fluctuation, so to deal with the quantum many-body problem, we have used mainly two numerical methods. One is exact diagonalization for small system, and for large system we have used the density matrix renormalization group. And using DMRG, we have calculated the spin gap, charge gap, different order parameter and the correlations. So, and here is the fruit of that labor. You can see we have the well-known phases like spin density wave phase, charge density wave phase and bond order wave phase. Along with that, we have a new exotic kind of phases, and which is the CDI, charge density wave 3 and ferroelectric. And I will explain all of these phases explicitly in the next few slides. So first comes to the ferroelectric phase, and it originates from its atomic limit. And you can see its periodicity 3-side periodic charge pattern. However, it is extremely fragile. because as you introduce the hopping T, the order parameter directly jumps to its value 0, which tells it is a first order phase transition. So it's a classical state struggling to survive in a quantum world. Next comes to the most interesting phase in our phase diagram, which is the charge disordered insulator phase. Let me break down why this is so unusual. First of all, it is an insulator because the charge gap is finite. But the central charge shows that it has a gapless spin excitation, so much like a Mott insulator. But here is the puzzle. So the charge-charge correlation shows that here there is no such long-range charge order whatsoever. And even more puzzling thing is that here double occupancy is so high that effective on-site local attractive interaction is generated. So it's an insulator that is not a Mott insulator, that does not have any long-range charge order, and even more, there is a local effective attractive interaction is generated, which does not fit into any standard phases. So the next question is that what's the mechanism? The answer lies in frustration. If you see the wave function carefully, you can see it's not completely random. It's a quantum superposition of various short-range charge order states, like little patches of charge density wave 1, charge density wave 2, ferroelectric, and all are competing with each other. And they prevent the electron moving throughout the whole system coherently. And that's why it's an insulator. So it's a frustration-induced localization that prevent the electron moving throughout the whole system, and it is not a Mott insulator or any long range charge order is generated. Now the last exotic phase in our phase diagram is the charge density wave 3, so which is fascinating in the opposite way. Here frustration does not destroy order, it creates a new one. Out of all completing classical state, quantum fluctuation creates a new long 8-side periodic charge order state. And we can confirm its long range periodicity from this charge structure factor P and also the order parameter. And here the spins on this charge form an alternating spin parallel like of state, which has a very small but a finite spin gap. So these are the all exotic phases which we obtain. The most interesting thing is the ferroelectric, CDI, and charge density wave 3. So the ferroelectric has a fragile classical remnant, and CDI is an gapped, and which is not a Mott insulator and does not have any long range charge order, and it's a new kind of phases which we obtained. And charge density wave 3 is a long 8-side periodic charge order states. So in summary, so charge frustration driven by the polarization effect is a powerful and previously underappreciated mechanism for stabilizing the exotic phases, and we will obtain the mainly 3 phases which is very exotic in nature, mainly CDI, charge density wave 3, and ferroelectric, and it provides a new theoretical framework for understanding phenomena in a low dimensional material where polarization is important, from organic conductors to certain oxide. And in future we hope that experimentally one can also find this type of phases, and even the deeper theoretical classification of these CDI phases is still we need to find. And I need to thank my group members, my supervisor Professor Manoranjan Kumar, my collaborator, and the funding agency and the host institute. So our paper has been published in PRL recently, and thank you for your kind attention.
Thank you, Shobhan. We have a minute for a quick question. Okay.
Thanks for a nice talk.
Yeah, thank you.
You had a state in which there is charge gap, but there are no spin gap, you said.
Yes, there is no spin gap, yes.
So, but they are localized spin-on excitations. They
Yes.
cannot be propagating because the background is disordered.
Yes,
So they are localized gapless excitations.
yes.
Okay. So, in the interest of time, let's move on to the next talk. But before that, let's thank Shobhan once more.
So I'm going to talk about our recent work on the relations between density-density correlators of states in the maximal spin multiplet. So this work is done with Ajit Balram. I also like to acknowledge the funding agency ANRF and IMSC for all the computing support. So as you know, the pair correlation GR, so that measures spatial correlation between particles. But computing the GR becomes challenging when you're in a strongly correlated setup. one typically can compute that exactly for small number of particles using exact diagonalization, but so you cannot go beyond a small number of particles. So if you have a candidate state, you can do some Monte Carlo calculation and you can get some nice results. But when you incorporate spin or pseudo-spin degrees of freedom, then it becomes again very challenging, and you cannot do a lot of numerics, and you cannot explore a lot of parameter space. So, but we know that a spin S state that has this 2s plus 1 fold multiplet. So each of these state in this multiplet has distinct correlators, but we know that we can actually traverse the spin multiplet using ladder operators. So we asked the following question, that what is the relation between density correlators in this multiplet? So, I'll give you a more formal definition of the pair correlation function. So let's say psi is a wave function for a translation and rotational invariant state with n particle and density rho naught. So the way you compute the pair correlation function is you put one of the particles at the origin with let's say spin sigma prime, and another one at a position r with spin sigma, and you integrate over rest of the spins and the position of the other particles. So now let's say in the this S is equal to n by 2 multiplet, which is the maximal spin multiplet for n number of particles. We let's say know the GR of the highest weight state, which is the state with quantum numbers S and Sz equal to n by 2, and we want to get the pair correlation function of the all other states which have these quantum numbers S n by 2 and Sz which are smaller than n by 2, right? So we found that there are some nice relations that you can use here. So on the right hand side, these GRs, these are the pair correlation of the highest weight state, and then on the left hand side we have pair correlation functions of this particular state which has Sz smaller than n by 2, and there are this some simple looking factors you have to multiply. So it is just rescaling of the original pair correlation of the highest weight state, and so physically this scalar this factors are nothing but these are ratios of number of pairs of a given flavor divided by the total number of pairs. So you have to do it for each flavor differently, and you basically generate the pair correlation for all different flavors for a given Sz. Okay, so now let me. So we wanted to use this, and we want to try out some calculations. So we thought that okay, we can maybe apply this to spin polarized fractional quantum Hall states. So there are some well-known examples that we can look into. So Ajit has already introduced, I mean, a lot of wave functions in the morning, but so I'll not spend a lot of time here. So this is basically this Laughlin wave function, which you can thought of as the highest weight state in the S is equal to n by 2 multiplet. So later on, so Halperin introduced or generalized Laughlin's wave function for spins. So now you can see that there are these 3 factors which has additional spin labels. So each factor looks like a part of the Laughlin state. So this is called the Halperin MMM state, which is a candidate state for filling factor 2 by m plus n. So let's say I want to apply this expressions that I showed you. I want to apply this to compute the pair correlation functions for Halperin MMM state for a given polarization, right? So let's say I fix the n up and n down. Okay, that fixes the polarization. And as I already said, the highest weight state is the Laughlin equal to 1 by m state. And basically on the right hand side I have this pair correlation of the Laughlin state, and I would multiply appropriate factors to convert it to pair correlation functions of the Halperin state. So let's try it on the Halperin 111 state. So this state is a good candidate for excitons, exciton condensation, but I'll come back to that later. But so we know for nu equal to 1, which is the highest weight state for the Halperin 111 state. So we know exactly this is the pair correlation function. And then, so let's say I want to compute the other pair correlation functions at this polarization. So I have to just scale this with appropriate numbers, and this is basically I have generated the pair correlation functions of all different components of this pair correlation, right? So So you can do for this for other states as well. So I'll show you another example for the Halperin 333 state. So in this case, the highest weight state is just the Laughlin 1/3 state, and then you do the same game. You just multiply this proper factors to get this polarization, some polarization. In this case, this is 1/3. So you will generate all these different components of the pair correlation function. So you can actually use this in. You don't have to really think about real spins. So this is also applicable for different pseudospins. So for example, you can think about layer pseudospins. So think about a bilayer setting for two component fractional quantum Hall. So we have now, let's say, two layers which are separated by a distance d, and the up and down these indices, they are now leveling these two layers. Okay, and in this case, you can think we are using a standard Coulomb interaction, so which is 1 by r in the same layer, and between these two layers, it is 1 by r square plus d square. So so we can basically compute the energies once you know this pair correlation function. So you just plug your different pair correlation functions here, you will just get all of the energies. So one nice thing that we could work out is the analytical energy of this Halperin, Coulomb energy of the Halperin 111 state. So this, so the gamma here is again this polarization. So in this case, it is a number imbalance between these two layers, and you can see this is so the d is the distance between these two layers. So basically, in the plane of gamma versus d, so this is an exact expression. So and this is I mean this numerical plot of this energy, as you can see. So there are some nice features, I mean, which you can directly see that d equal to 0 when these two layers are on top of each other. There is no dependence on the polarization, right? Because two layers are basically single layer, and at polarization 1, all of the particles are on one of the layer. Let's say that only the top layer. And then, so there is no distance dependence of that state, right? And so as you go to this intermediate values of polarization and slightly larger values of d, you see that so there is an increase of energy. So it's because we are taking this candidate states and at this kind of parameter regime, it cannot very efficiently minimize the Coulomb energy. So this energy has a slightly increase. So at this point, this system will transit to some other state which has a lower energy than that. But so this is so additionally, you can do this for also Halperin 333 state. Qualitatively, you are going to get similar kind of energy in the gamma versus d plane. The numbers are all different because they are happening at different filling factors. So I will just like to emphasize here that this kind of computations previously would have been very much computationally expensive, because you have to compute the energies at each point in this diagram, right? And then you have to do Monte Carlo calculations or some other calculation at each point, and that basically becomes. Yeah. You have a minute. Okay, I'll finish just in a minute. So basically, you can compute these energies for spin polarized state using these formulas. So you can also write down similar expressions for structure factors. So you just need the structure factor of the highest weight state, and then you can basically write down structure factors of the all other states in the multiplet. So I'll just quickly summarize. So we have provided some exact identities to obtain correlators for the entire maximal spin multiplet. We have also computed phase diagram in the gamma d space. So the formulas that I have shown you is applicable for both fermionic and bosonic systems with maximal SU2 spin or pseudo spin degree of freedom, and this naturally extends to some SUQ systems, for example SU4 or SU8, which is like relevant in graphene and bilayer graphene. So thanks, that's all.
Thank you. Quick question. Okay, if not, let's thank the speaker to close his talk and move on.
Hello all.
Do you have phone with you?
I don't have my phone. Hello. Hello. Okay. I think it'll be fine. Okay. So sorry about the mishap. So I'll be talking about non-abelian braiding and you know what? I'll just hold it in my hand. So I'll be talking about non-abelian fusion and braiding in many-body pattern states. This is a work that I did while I was at IMSC during my PhD, and now I've shifted to the Lodha Theoretical Physics Institute. So some background, because the audience is not primarily from fractional quantum Hall effect. So the system that we are looking at is a electron gas that is confined to 2 dimensions and subjected to very strong perpendicular magnetic field. Now classically, we would see that the resistivity of the system increases linearly with magnetic field, but as the system is cooled to cryogenic temperatures, we see that the resistance or the resistivity is plateaued over a range of magnetic field. And we see this plateau is actually can be integer or fractional up to very good accuracy. And what we are going to talk about today is in fractional quantum Hall effect. But a remarkable phenomena as this is because this is not like a quantization of a specific variable, but a property of the system which has disorder. And you see this phenomena across samples of different materials as well. So that is quite remarkable about this system. Now going on to the physics part of it, it's essentially minimizing the Coulomb interaction, and that is quite a tough problem given that the Coulomb interaction will choose a unique ground state, will arrange or will break the degeneracy in an extensive Landau level and choose a unique ground state. And that is kind of problematic if we want to numerically solve it. But what the community has done is it has come up with really good ways of solving this problem, and one such being the many body wave functional ansatz. So one such theory is the composite fermion theory, which states that, I have a very tough problem of interacting electrons subjected to very strong perpendicular magnetic field. Why don't I treat it as non-interacting? So composite fermion theory maps interacting electrons to non-interacting composite fermions and writes the many body wave functional ansatz, which is not only analytically very beautiful, but also qualitatively very accurate, quantitatively as well, but qualitatively also very accurate in terms of what we see in experiments. But as sample quality improved, many filling fractions beyond the JN sequence were observed, and that called for a more general theory, which is known as the pattern theory. So what composite fermion does is that it puts a restriction that each electron needs to have an even number of flux vortices. Now we take another approach where we say, I will break my electrons into partons, each of which will have different fractional charges, and they will fill their individual integer quantum Hall states, and together I'll put them back and write the many body wave function. So this is also a many body wave functional ansatz, just in a different approach. And how do we come up with these parton states? They are usually for a filling fraction, there are certain constraint equations, like saying all the partons will see the same density, the charge of all the partons will add up to 1. And so there's one such example for half, which is also originally that Jan had proposed. Now moving on, the parton construction by itself accommodates excitations, which can be thought of as quasi-holes, leaving an orbital empty in the topmost filled effective Landau level, or filling one orbital as such. And these naturally give fractional charges, which can be either positive or negative, and depends on what filling fractions we are looking at. And they have fractional charge. Now, if I told this to you just by saying this, it might look like it's just a renormalization or an effective theory giving some property, but don't take my word for it. Experiments have actually, and it's been quite some time that experiments have seen these fractionally charged particles. But even beyond, so this experiment happened about 2 decades ago, but even beyond that, signatures of these 2-dimensional objects were kind of expected from topology. So in 3 dimensions, topology allows permutation symmetry of plus and minus, which corresponds to bosons or fermions. But in 2 dimension, topology allows any value from 0 to pi. So if I exchange or if I braid any 2 anions in 3 dimensions, I'm supposed to get 0 or pi corresponding to plus or minus. But in 2 dimensions, if I work with 2-dimensional particles, then I'm supposed to get any infinite value between this range. And what is a better system to look for this phenomena than the fractional quantum Hall effect, which has emergent 2-dimensional fractionally charged particles. But now and this has also been experimentally seen recently in the past 5 years. But let's now go ahead and generalize this further. So what if I say I braid this and I do not come back to the same state, but I now map to a different state. So it's just not a constant phase factor that I'm getting. I'm also mapping the entire wave function to some other state altogether. And this was actually known theoretically from effective field theory. Which was first proposed by Venn. So he showed that in pattern states of the form phi nm, so this is crucial, there are n copies of phi n, is described by SU, so n level SUM Chern-Simons theory in the bulk, and by bulk boundary correspondence, it follows an SUNM with Zubino-Witten, WZW, CFT at the edge. And this CFT correlators can actually be used to form many-body wave functions in the bulk. So that is the many-body wave function. And by level rank duality, so this once you show that this effective field theory is explained by n-level SUM Chern-Simons theory, all the rest follows. So there's also a notion of level rank duality, which says that these two states, although quantitatively very different, will have the same anionic data, like fusion rules, braiding data, etc., etc. So for example, if I take phi 2k, it's described by level 2 SUK Chern-Simons theory. We apply bulk boundary correspondence, and we get this SU2K WZW CFT, which also has like a ZK parafermionic CFT description. And then the level rank duality tells us that phi 2K and phi K2 should have the same anionic data. Now the point of saying this is, this was done in and around 1991, I think, and this was known from effective field theory, and effective field theory essentially integrates out all microscopic coordinates. So we don't really know how the electrons are behaving or what are they doing microscopically. So although pattern states, a lot of studies have been done in pattern states, and excitations have been studied extensively in pattern states, but excitations of the kind which obey the CFT, the fusion rule and braiding statistics, have not been shown. So in this work, I come up with an ansatz which builds on coherent state constructions that are done in composite fermion theories before. And
you have a minute.
Okay, right, okay. So I'll hurry. So this is the central result. I'll just skip the map. And what I show is that now if I take any phi nm value, and I can have any quasi-holes and I distribute them. So the idea is, even if we had coherent state, there are certain subtleties. One is how we distribute them among the same copies, that if I have m copies of phi n, this is crucial because when we say there's an SUNM kind of symmetry in the system, the gauge degeneracies between them actually give that property. So it's important to realize how to do the distribution. And there are also some anti-symmetric principles that need to be taken care of. And once I did that, we could show that that these wave functions, variational wave functions, just don't match CFT, but also show level rank duality for the first time. And I also computed braiding statistics for few cases and showed that it matches CFT data very well. So the error is decreasing. So I'll just take, and yes, it also shows CFT data for states where the fusion rules have not been worked out. So it's not known theoretically. So finally, why is this important and why should people care about it is because the concept of non-abelian topological quantum computation has been in theory for a really long time. But what experiments show that rather than getting the expected fractionally charged particles or fractional braiding statistics, a multiple of the value is seen. And this is kind of attributed to clustering of anyons. So all the anyons are same like charged particles. Since they are emergent particles, they have oscillatory behavior and they can choose even though they are same charged. And so what happens is that it can obscure this nice CFT properties. Since pattern states can accommodate abelian and non-abelian kind of charged particles, we hope that now using this many-body wave function, we can write, do the energetics and see why is what we are seeing in experiments. Thank you.
Thanks. Is there a very quick question? Okay.
So the clustering of anions is equal to clustering of partons. Is that correct?
Yeah, I couldn't hear you.
Clustering of anions,
Yeah.
you connect it to clustering of parton as excitations.
Clustering of anyons in the last.
Yeah. So are they connected to clustering of parton?
No, they are not. They are not connected to clustering. So they are in some sense partons, like they are fractionally charged particles, you can call them partons, but the clustering occurs, you can't really understand directly from the many-body wave function.
Partons also you cannot directly.
No, you cannot, but because it's kind of counterintuitive because they're fractionally charged. There have been energetics that show that they should be stabilized, but we don't really fundamentally understand why that should be. There are few proposed theories that since they're oscillatory, the oscillatory tails can kind of overlap in a way that it minimizes their energies. But again, it's also dependent on what kind of interactions we are looking at, whether there is quantum well, whether there is disorder, Landau level mixing, etc., etc.
Okay, with that, let's close the session by thanking our speakers.